is there a relationship between pressure of a gas and solubility of a gas in a solution? So this is a can of Coke. You have Coke, and inside this, above Coke, there is carbon dioxide. The pressure of carbon dioxide is about 2 atm in a can of Coke. So when you open a can of Coke, what do you hear? Do you hear psst? What is that? Is that telling you that pressurized carbon dioxide is coming out? So the pressure of 2 atmosphere, 2 atm, is reduced to pressure of 1 atm. So guys, if you open a can of Coke and leave it overnight, is it going to go flat? Why? Because look at number of CO2 dissolved. The blue dots, number of CO2 dissolved in Coke.
Is that because there's no way to keep the pressure contained?
Correct, because you're reducing pressure. Look, what is happening? You see the blue spots are reduced. So can I say solubility of a gas in a liquid depends on the pressure of the gas above the liquid? Higher pressure, higher solubility, lower pressure, lower solubility. This is Henry's law. It says solubility of a gas inside the solution depends on the pressure of the gas above the solution. So you may say, who cares about Henry's law? Who cares about the can of Coke? How about our being alive, breathing in, and taking oxygen to our cells and staying alive? That is following Henry's law. How? These are alveoli, air sac in our lungs. And the pressure of gases inside our lungs and alveoli can be adjusted by changing the volume, right? Volume and pressure are inversely related. So the pressure of oxygen in our alveoli is adjusted to be 100 millimeter of mercury. And there is carbon dioxide kept at a pressure of 40 millimeter of mercury. So when oxygen depleted blood in our vein is coming in contact with the surface of the alveoli, is it fair to say that carbon dioxide is moving from higher pressure to lower pressure, from 46 millimeter of mercury, which is higher than 40 millimeter of mercury? So carbon dioxide is going to be released from our vein. And look at the pressure of oxygen, dissolved oxygen in our vein, 40 millimeter of mercury, pressure of the oxygen inside alveoli 100. So when these are in contact together, oxygen is going to move from higher pressure to lower pressure. And carbon dioxide is going to move out from our vein into the alveoli. So the result is now you have oxygen-enriched blood going by the heart, pushing by the heart into our veins. And look what is the pressure of these gases inside our vein. Oxygen 100 millimeter of mercury, carbon dioxide is now adjusted to be 40 millimeter of mercury. And what happens at here? At the surface of the cell, you see the oxygen pressure less than 30. So oxygen moves from higher pressure of 100 into the cell. And inside the cell, pressure of carbon dioxide is more than 50 millimeter of mercury. Inside the vein is 40. So at the same spot, carbon dioxide is moving in, oxygen is moving out, and this is what is happening. Our vein is carrying carbon dioxide to the lungs, releasing carbon dioxide, absorbing oxygen, and delivering to our cells. So this is application of Henry's law. Solubility of a gas inside a solution depends on the pressure of the gas above the solution.
So the higher the pressure, the higher the solubility, and vice
Excellent.
versa.
Yes. Do you see?
Okay.
This is on the left. You see higher pressure, and do you see more blue spots, more carbon dioxide dissolving the core. Now, on the right, we open the can. The pressure is not 2 atmosphere anymore. The pressure is adjusted to be 1 atmosphere. So the pressure is reduced. As a result, number of the carbon dioxide dissolved in coke is also reduced. So the solubility of a gas above the solubility of a gas in a solution depends on the pressure of the gas above the solution.
So if you were to take like a Coca-Cola can way up to Mount Shasta and open it up there, would it take longer for the carbon dioxide to come out, to be released, because there's a higher pressure up there?
Actually, no, actually the pressure is lower at Mount Shasta. The higher elevation you get from ground, the pressure goes down.
Oh.
Yes, so pressure is 1 atmosphere at sea level. In Reading, we are 800 feet above the sea level. The pressure is a little bit less than atmosphere. On the tip of Mount Shasta, where the elevation is higher, the pressure is going to be lower than atmosphere. Would be 650.